All right, let's go ahead and get started. My name is Saad Ali. I'm one of the co-chairs of SIG Storage, and today I wanted to take some time to talk to you about what the Storage Special Interest Group for Kubernetes is, what it does, how to get involved, and so on. And I have a few of the veteran members of the SIG here to help me out. They're going to be doing some presentations, and we're going to be doing a panel at the end. I don't think Ben knows that he'll be on the panel, but he will. All right, so again, here's the agenda. I'm going to go over just an intro to get you familiar with what the SIG is, and then Michelle's going to jump in and talk about Kubernetes and give you an update for CSI in particular. And Shing is going to be talking to you along with Sean Chen about VolumeSnapshots, which is being moved to beta this quarter. And then finally, we'll end up with a general Q&A with the panel. So what is the Kubernetes Storage Special Interest Group responsible for? We focus primarily on block and file storage. So if you're familiar with storage at all, you probably know about a ton of different things that are able to store bits, right? Your databases, message queues, so on and so forth. Not all of that is within the purview of the Storage Special Interest Group. What we're interested in is kind of where the rubber meets the road. Whether you have a message queue, a database, or some other managed service, ultimately it's going to need to write bits down to the disk, and the way that they do that is through some sort of file system or block device abstraction. And what we do in the Kubernetes Storage Special Interest Group is provide that abstraction such that regardless of where your workload is scheduled and regardless of who or what implementation is providing that underlying block or file, we make it available inside your container wherever it's scheduled. And so this involves, at the very bare minimum, the ability to automatically provision block or file storage through the Kubernetes API, the ability to have it attach and mount and being made available inside the container wherever your container is scheduled, and then, of course, move around with your pod as your pod is shifted around for whatever reason across a cluster. We also have interfaces that allow the Kubernetes scheduler, for example, to influence where a particular volume is going to be provisioned. If you have a storage system that is not available equally to all nodes in a cluster, for example, you want the scheduler to be able to take that into account when it's making a scheduling decision. So we have logic to enable that. And of course, doing things like storage capacity management. So you as a cluster administrator can define how much storage is available to particular subsets of users and how large a volume they are able to carve out and things like that. So storage management. Moving on, some of the notable examples of the things that our SIG owns you're probably familiar with are persistent volume claims, persistent volume, storage classes, dynamic provisioning, and much more. We also own the interfaces by which Kubernetes interacts with storage systems. The biggest one that we have and the one that we're moving into the future with is called the Container Storage Interface. This was GA'd as of Kubernetes 1.13 in December of last year and is since maturing and adding more and more functionality, and Michelle's going to tell you a lot more about that. We're also responsible for ephemeral volumes, all right? So you're familiar with traditional persistent volumes where your data is persisted off on some data store, and if your pod dies and comes back up somewhere else, that persistent data is persisted on a, for example, storage array or a cloud volume of some sort. But we're also responsible for ephemeral volumes where you could have information that is temporary. It's created when the pod is started and then deleted when the pod goes away. So the traditional example of that is what we call an empty dir. It's scratch space that can be shared amongst all the containers in a pod. And then we build on top of that with secret config map and downward API volumes, which are basically taking an empty dir and pre-populating it with some data so that it's easier for your application to consume. So your application may not know how to talk to Kubernetes to fetch a secret, for example, but it probably knows how to read a file in order to extract a secret. So what the secret volume allows you to do is point to some Kubernetes secrets and have those surfaced inside your container as a file that your application can then read. The goal of this is try to meet users where they are. So there's a lot more we're responsible for. Everything about our team is documented on this GitHub page. If you go there, you're going to find all the projects and repos for the code that we're responsible for, as well as the mailing lists, team meetings, and so on and so forth. The SIG is very, very large. We held a face-to-face meeting on Monday here at KubeCon for folks who are contributors to the SIG, and we had 60 attendees, and we had to cap it at 60 because we ran out of space. We have folks from all over the industry, lots and lots of storage vendors, lots of cloud providers, and pretty much everything in between. So what does this SIG do? So we're responsible for this kind of storage layer, but like, what do? We show up, and ultimately what we do is write code. We write code to enable these features, we write tests, we fix bugs, all related to the volume subsystem. And the way that we do this is that we have a virtual meeting on Zoom every 2 weeks, and we use that meeting to kind of keep track of what the SIG and the members of the SIG are working on, what the status of the projects are that we care about, and then also planning what we're going to do next. And then again, we also meet face-to-face, so we just had this face-to-face meeting last week. We try to do that about every 1 year or every twice a year. And the purpose of that is just for folks to be able to see each other, figure out who's behind the GitHub name, socialize, but also try to drive forward some of the bigger design discussions that you can't really make progress on in a 1 or 2 hour video conference call. And we found those to be very, very useful as well. And the SIG is accessible via a number of means. There is a mailing list, Kubernetes SIG Storage Google group that you can join to ask questions, to see what folks are asking about. There's also a Slack channel. There's actually multiple Slack channels. We have the SIG Storage Slack channel where you can come in and ask questions about anything. There's now a CSI channel. There's a CSI migration channel and a CSI Windows channel as well. These are sub-areas and sub-projects. If you have specific questions, you have folks in those channels that can help answer your questions. So the community tends to be pretty responsive. So what have we been working on? In Kubernetes 1.16, we moved a number of features to beta. I talked about CSI and how CSI was GA'd in the 1.13 release. CSI is kind of the platform that we're building on top of. So for all additional functionality, we're adding it to CSI. The big features that went into the last release were volume cloning, volume expansion, and ephemeral volumes. Volume cloning is the ability to say, hey, I have a PVC, I want to create another PVC that is an exact copy of this, and with the hope that the storage system can do that efficiently. Volume expansion allows you, through the Kubernetes API, to say, hey, I started off with a volume of a specific size, maybe 100 gigs, but I'm running out of space. Please expand the size of this volume to 200 gigs so that if you are hitting limits or whatever, you can address that through the Kubernetes API. And then finally, CSI ephemeral volumes have also been moved to beta. I talked about secret config map, downward API, and empty dir volumes, which are built into the core of Kubernetes. We wanted folks outside of the Kubernetes kind of core team to be able to build such volumes using CSI as well. And so there's a number of features that went into CSI to enable that, and that functionality has been moved to beta as well. So for this quarter, 1.17, we have a number of features in progress. We're moving CSI topology to GA. This is a big milestone for us. CSI topology is all about realizing that a storage volume may not be equally accessible to all nodes within a cluster. And this could be for a number of reasons. You could have something that's local to a given node. It's a disk that's attached to only one node, and you can only use it on that one node. It may be that you have a storage array, or you're running in a cloud environment where a particular volume is available in a specific zone. Only nodes in that zone can access it, but your cluster may span multiple zones. So to In order for the Kubernetes scheduler to make intelligent scheduling decisions, we've introduced a number of features around here that we're calling topology, and specifically we're adding that to CSI. Next up is the volume attach limits. So this is kind of a smaller feature, but it's very important. The idea here is that a given storage system may have limits on the number of volumes that can be attached to a single node. And if Kubernetes doesn't know about that, it may schedule more than that number on a given node and end up with pods that aren't able to start. And so this functionality allows the storage system to bubble this information up to Kubernetes so that the Kubernetes scheduler can make intelligent decisions about scheduling based on that. We also have a couple of features that are moving to beta. The biggest one is CSI VolumeSnapshots. This is a feature that has been requested for a very long time and has been in development for a while. And there's a lot of work going on here that Xing and Sean are going to be sharing with you later today. But the kind of high level here is a lot of storage systems support the ability to take some sort of point-in-time capture of what you have on disk so that if something goes wrong in the future, you can revert back to that state. And they're able to do that efficiently on disk. And so with Kubernetes, we wanted to expose the ability to do that through the Kubernetes API so that, for example, if you're a database administrator and you're going to do something weird that you're not sure is going to work, you can make that risky change, but before that, you can create a snapshot through the Kubernetes API. If something goes wrong, you can always roll back. And then finally, we have what we're calling the CSI migration effort. So before CSI existed, we had a couple of different ways to create volume plugins for Kubernetes. First was in-tree, and the second was flex. In-tree meant that the code for how Kubernetes interacted with the volume subsystem was actually built into the core Kubernetes binaries. So initially, you're probably familiar with the volume subsystem. It's all built into the Kubernetes API. You specify a volume and then a type of volume. It could be something like a GCE persistent disk, an AWS volume, or some other type of storage volume. They're all encoded, hard-coded into the Kubernetes API. And that was the old way of doing things. The problem with that approach was that it wasn't scalable. It required all that third-party code to live inside the core Kubernetes repo. It was very difficult for the maintainers of Kubernetes to actually test. And it also caused security vulnerabilities where if there is an issue with one of these extensions, they could crash core Kubernetes components. And so we wanted to get away from that, and our first attempt at doing that was something that we call flex volumes. Flex volumes was very basic. You had a file. It could be an executable. It could be a script that handled a handful of commands, mount, unmount, and I think there were a couple others. And it got the job done, but it also had a number of challenges, especially around deployment. The way that it worked is that you had to deploy the Flex driver as a file that needed to be copied to the root file system on every node in your cluster. And as you can imagine, that can be pretty daunting and difficult to manage. All the problems that Kubernetes solves for applications in terms of upgrade, downgrade, deployment, Flex Volume didn't really solve that for itself. So how do you deploy all these files? How do you keep them up to date? And all of that was a challenge. Our second attempt at this was CSI, and that's been much more successful. CSI allows you to deploy a plugin, a storage plugin to Kubernetes, just like you deploy any other workload on Kubernetes. You can do kubectl apply some YAML, and you've taught Kubernetes how to interact with a new storage system if you have a new storage array or whatever. So it's a much better approach, and it's been pretty successful. We GA'd in Q4 of last year, December of last year. So the original in-tree volume plugin existed in Kubernetes 1.0. So from 1.0 to 1.13 was almost 3-4 years. We ended up with about 20 in-tree volume plugins. And then from December to now, we now have 50 CSI drivers. So it kind of opened up the doors and let everybody come in and integrate with Kubernetes more easily. So moving on, let's talk about how do you get involved. If you are interested, again, go to the SIG Storage page. You're going to find all the information on there. Our bi-weekly meeting happens at 9 a.m. Pacific time every second Thursday. It's a Zoom meeting. You can turn your camera on or not, whatever you like. There's an agenda doc that we link to. Feel free to add content to that. If there's something that you want to talk about, throw it in the agenda, and then we'll make sure that we get to it during the call. The next meeting is going to be December 5th. We skipped the meeting this morning because we had a face-to-face on Monday. And if you're interested in contributing, start familiarizing yourself with the code. Just, I like to start with the main method and try to understand how the code works. With Kubernetes, that can be pretty daunting. But I'd say look at the kube controller manager and look for the attached detached controller, or look at the volume manager code in kubelet. Jan is up here giggling because that code is non-trivial, but it's a good place to start, just familiarizing yourself. And then when you feel comfortable, start with fixing a bug. I took a look a couple of weeks ago, and there were 272 open bugs in Kubernetes that were marked with SIG storage. So there's a lot of work that is left to be done. If you want to figure out which ones to help out with, there's also a help wanted label that you can filter by and use that as a guide for where to begin. And of course, talk to us, the folks who've been in the community for a while. We'd be more than happy to help you kind of on board. You can reach us through Slack. You can reach us through the Zoom meetings. You can send us messages on the Kubernetes Storage SIG Google group. We'd be happy to get you ramped up. So start by writing tests, and once you become more comfortable, you can start taking on larger features. We do quarterly planning for every Kubernetes release. This happens at the beginning of the quarter. For the 1.18 release, it's going to happen at the end of December. And when we do that, we say, what are the things that folks in the SIG are interested in working on? People often ask, like, how does a SIG figure out what it works on? Like, who decides? Whose decision is that? Is that my decision? And ultimately, it's not. It's the people who show up to the SIG and decide to write code, right? It's the people, it's you. You show up and you decide what you work on, and that's what the SIG works on. And so we try to just guide that through this planning process to say, okay, who's committed to working on what? Put their name down. And then throughout the quarter in our Zoom meetings, we'll keep track of what folks are working on and what the status of their project is, and make sure that the SIG release and everybody else in the community knows what's going on, make sure that all the other processes are happening, the documentation's getting written, the tests are getting written, so on and so forth. We keep track of that all in this planning spreadsheet, which you can find a link of in the agenda. And then the process for how you introduce a feature into Kubernetes is kind of two parts. You need, in terms of process, you need an enhancement issue to keep track of which release a particular feature is going into. This gives folks outside of the SIG an idea of what features are going into a particular Kubernetes release. And the second part of it is a KEP. This is basically a design document that's a proposal for, here's a new feature I want to implement, here's how I'm going to implement it, here are the alternatives I've considered, here's what the API is going to look like. And once your KEP is approved, then it moves on to the implementation stage. We do need more contributors, so I see a lot of you in this room. If you're at all interested, please reach out. We'd love to get you involved. There's a handful of very dedicated contributors who've been working very hard, but there are a ton of features that everyone is asking for, so the more people we have involved, the better. At KubeCon, we happened to be one of the last presentations, so this is a little bit backwards, but there were a number of presentations that happened that were storage related, both on Tuesday and Wednesday. You can find the recordings for these online. And there's a ton of material from past KubeCons that was also recorded that you can find online as well. I highly recommend you go through these if you're interested at all in SIG storage. And that's all for me. I'm going to hand it over to Michelle to give an update on CSI.
All right, thank you, Saad. All right, so I'm gonna give an overview of basically all the CSI-related features that we have done and what we are currently working on, and also kind of give an idea of what we have in store in the future. First, as some general background, one of a major effort that we've been trying to take on in the CSI group is to improve the experience for people to write CSI drivers. So the main documentation page where you can find all the information about what it takes to write a CSI driver is up here at kubernetes-csi.github.io. And we have a sample driver that you can also take a look at if you just want to get started and you just want to like copy paste something and start from there. In addition, other resources you have as a driver developer is around testing. And we currently provide two main types of testing that you can use on your CSI driver. First is what we call CSI Sanity. And the purpose of this test suite is to test how well your driver conforms to the CSI spec. And it tests some positive test cases, but it mostly tests a lot of negative test cases, like is your driver returning the correct error codes in these specific error conditions? Sorry. So that's sort of testing conformance to the CSI spec. If you want end-to-end testing in an actual Kubernetes cluster and get like functional tests that way, we also have an E2E test suite that runs against any Kubernetes cluster and any CSI driver, and it runs about 30 or so different test cases. So I would highly recommend taking a look at this to actually test out your driver against Kubernetes. We've tried to make the process as streamlined as possible. Mainly, with every Kubernetes release, there is an E2E test binary that is made available as one of the release artifacts. And you just need to download that E2E binary, define a simple YAML file with some information about your CSI driver, like what storage class you want to test against. And then you just run that binary with one command, and then it'll run a bunch of test cases there. You can take a look at the documentation that we have for more instructions on how to get that set up. All right, so now I want to kind of highlight a couple of really cool features that have gone into CSI over the past couple of releases. First is CSI migration. Like Saad said, this went beta in 1.17. So what exactly is CSI migration? The idea with CSI migration is that you can, we end up servicing in-tree volume APIs with a CSI backend. So today, if you use volumes like GCE persistent disk or AWS EBS in Kubernetes, you're using an in-tree volume API. Now, this is sort of a joint project with SIG Cloud Provider, and the idea is that all cloud provider specific code is going to get removed from Kubernetes in about a year time frame. So normally, something like that would be considered a breaking change because the API you were using before no longer works when all of the code behind it is removed. So the idea with CSI migration is that we can continue to keep those APIs working with the in-tree volume APIs, but the only difference is actually being serviced by the equivalent CSI driver. So that is kind of like an overview of what CSI migration is. Our first phase of CSI migration is to migrate all of the major cloud provider drivers that are currently built into Kubernetes. So to give a summary of the timeline on current status on each of the cloud providers, we have just betaed the feature with the AWS EBS and GCE PD drivers. The other remaining in-tree cloud providers, OpenStack, Azure, and vSphere, are still coming along. But we're kind of working backwards from the deadline set by SIG cloud provider, which is by 1.21, all of the cloud provider code will be removed. So kind of working backwards from there, we kind of arrived to this timeline for feature graduation. So if you're interested in trying out this feature, there's two ways to do it. If you're using a managed service like GKE, EKS, or AKS, you don't have to worry about this. Your managed service will take care of enabling CSI migration for you seamlessly. Now, if you are self-deploying your own Kubernetes on one of these 5 cloud providers, then you will have to take some action. First, from the CSI's perspective, you need to install the CSI driver in your cluster, turn on the CSI migration feature gates, and then from there you're basically trying out the feature. Now this is, like I said, this is part of the bigger overall cloud provider extraction effort. So one of the goals that we have is to put all of those CSI deployment details into the main external cloud provider repositories. So that way you don't have to separately deploy the external cloud provider controllers and the CSI driver. You can just go to one repo and deploy everything that's there. And if you want to get involved with the project, we have a special Slack channel in the Kubernetes Slack, which is CSI-migration. All right, the next feature I want to highlight is CSI Windows. So we have an interesting problem in that Windows containers can't actually be privileged. And this is a problem for CSI drivers because they have to do a lot of privileged operations like mounting disks, creating disks, and that kind of thing. So the way that we have solved this for Windows is to come up with a new CSI proxy binary which runs directly on the host as a binary, not a container, and have that binary perform all of the privileged operations on behalf of the CSI driver. So in order to use this, the CSI proxy exposes a set of gRPC APIs, and CSI drivers have to be aware of these APIs and communicate to the proxy using them. Currently, we have planned APIs for most of the common file and block storage protocols, like Samba and iSCSI, as well as basic block devices. Currently, this project is under development. We anticipate having a complete alpha solution ready for testing in the next quarter or so. If this is something you're interested in, we have a special Slack channel for this as well, a CSI Windows. The next feature I want to highlight is CSI Ephemeral volumes. The main purpose of this is to allow inline volumes where the volume lifecycle is equivalent to the pod lifecycle. So these are things like today in Kubernetes, the ephemeral volumes we have are things like empty dir, config maps, or secrets. This is kind of in line with that, but it's CSI based, which means you can create a volume type or a volume driver for like anything you want. Some interesting examples of some ephemeral drivers are the image populator. This basically lets you mount any container image as a volume in your container. And then there's a couple of cool drivers around certificate management and secret storage from third-party storage like Vault. So these are really cool examples of ephemeral volumes, and I'm sure there's, this is basically going to open doors for all sorts of really interesting use cases. All right, And sort of to go over what we have in store in the future, we have a lot of features in progress, and our major goal for the next year is to drive all of these features to GA. So we have some features like, I'll just go down the list. The first feature is skip attach. This is mainly for CSI drivers like NFS, or file drivers like NFS, where they don't actually have an attach or detach operation. Right now, what you have to do is deploy the external attacher sidecars to them, but this feature makes it so that you don't have to do that, and it skips that whole code path. Next is pod info on mount. This feature basically passes in some pod metadata to your on every mount call. This is if your driver, wants to create some sort of like pod-specific secret or pod-specific authentication kind of thing. You can get that pod metadata on every single mount call. And then next we have raw block. This is a feature that lets you get access to the raw block device from a storage system instead of getting a formatted file system, which is what the default is today. This is a useful feature for things like databases or distributed file systems that might operate directly on a raw block device. Then we have cloning, which Saad talked about a little earlier. This is the ability to make a copy of an existing PVC. I think Saad also talked about resizing. This is letting you expand the volume size of a volume. And then snapshots is something we just betaed in 1.17. We are hoping to GA snapshots also within the first half of next year. And Xing and Shangchen are going to talk a lot more about this in more detail. And then, like I said earlier, we plan to have an alpha for Windows CSI drivers very soon. From there, for the second half of 2020, the other features we plan to graduate are ephemeral volumes and CSI migration for all of the cloud provider plugins in order for us to meet the 1.21 deadline to remove all in-tree cloud provider code. So that's sort of our future plans for features that we currently have outstanding and people are working on. At the same time, we are sort of investigating and prototyping more use cases and features, such as volume health. This is the ability to detect if your volume is healthy or not, and to sort of expose metrics and other states so that you can monitor your volumes and be able to react when your volumes become unhealthy. From an operational standpoint, if you are a Kubernetes operator or a Kubernetes cluster operator, we plan on improving the existing operational metrics that we have around the health of our Kubernetes controllers, as well as adding more metrics into the health of CSI drivers themselves, so that you can, at a fleet level, you can have better visibility into how the cluster is performing. Another feature that we are currently investigating is the notion of storage pools and the capacity of those storage pools. This is to help enable use cases like local volume dynamic provisioning, as well as the CSI ephemeral volumes sort of capacity management. And then I think Xing and Shangchen will talk about this in more detail later, but we're also looking at a lot of other use cases around snapshots and backups as well. So you can see we have a lot of work that we are doing in CSI. We definitely need all the help we can get. So there's lots, in addition to the all of the different features that I've been talking about, We also have community-maintained CSI drivers for common protocols like NFS and iSCSI. We're looking for contributors to help maintain those drivers. We are also looking at people to help with our whole testing and release infrastructure for all the different CSI common components that we provide to CSI plugins. So if you're interested in getting involved, we have the CSI Slack channel. Just go ahead and pop in and say hello. We're all pretty friendly people. And we also have, in terms of looking at issues, look for the help wanted label in our repository, which is Kubernetes-CSI. All right, so that's all I have on the latest happenings in CSI. I'm going to hand it off to Xing and Shanchen to talk about snapshots.
Thanks, Michelle. Hi, I'm Xing Yang. I work for VMware, and this is Shangchen. Both Shangchen and Jing work for Google. We work together on volume snapshots. So we added the volume snapshot support in 1.12, and now in 1.17, it's going to go beta. We made a lot of changes in the APIs, going from alpha to beta, and the changes are not backward compatible. And we also split the controller from 1 to 2. We will go into more details later. So there are two ways to provision volume snapshots: dynamically provisioning or pre-provisioned snapshots. So to dynamically create a snapshot, user will create a volume snapshot API object, which is namespace and is created with the PVC as a data source. That will trigger a creation of a physical snapshot on the storage system. And also a volume snapshot content object will be created to represent this physical snapshot. For pre-provisioned snapshot, admin manually create a volume snapshot content API object to represent a pre-provisioned snapshot, and user creates a volume snapshot API object, which points to the volume snapshot content, and then the controller binds them if the volume snapshot content points back to the volume snapshot. So before we dive into the details of the API changes, let's go over the API design principles. So usually in the API object, or in many API objects, you'll see a spec and a status. Spec represents the desired state. That could be configuration, settings, it could be some properties. And the status represents the actual state. It could be that will be the information updated by the controller. So when user first create a API object, status cannot be specified. It has to be updated by the controller. And also, we also should be able to recover the status if it's somehow lost based on the spec by the controller. So now I'm going to hand over to Shangchen, who's going to talk about the API changes and also the controller split.
Thanks, Shin. You just revealed my secret. Just so you guys know, before, I was a complete newbie when joined the SIG Storage a couple months back. And that's actually the first project I ever conducted. There's no reason for me to say no. First of all, it got all the attention, right? People need it. And secondly, it's really, really been there for a little while. So we want to push it up. And thirdly, it's really, I think it's gonna be simple like this, right? How many lines of code change you guys can tell? I can literally count it. To jump into all these API changes, every single change we made during the process is actually involves a whole bunch of discussion with the help of the SIG Storage, right? The first thing ever we did is to get rid of the source. If you're familiar with Alpha API, the source, it represents the PVC reference before. And now it become a union. It can come from a persistent volume name, or it can come from a snapshot content name. The major reason why we did this is we want to be able to distinguish between whether a volume snapshot is actually dynamically created or you are actually pointing to a pre-provisioned snapshot in the system. And then we went ahead and then removed this snapshot content name from the spec. The reason why, it's back to the API principles, which unfortunately were released ahead of us. You need to make sure your spec specifies the user wanted feature, and that field is actually a status. So if you notice that on the status, we added a field called bound, volume snapshot content name. And that's actually the paired content in the API server tells you, hey, this is your content. And that's basically a couple of lines changed in volume snapshot object. Let's move on to volume snapshot content. It's a very similar idea. Beforehand, we had a reference to a persistent volume. Actually, that's from where you take your snapshot. Now it becomes an option where a user can either specify, oh, I want to use an existing snapshot handle. That's normally your system admin's job. Or you don't even care what's in there. The controller is going to take care of it. The controller is going to go ahead and find the PVC and the corresponding PV and get the volume handle and put it over there. Again, we have this snapshot handle in the status. And that is basically the end result the controller observes at this point of time, what is the status of your snapshot content. One more thing I want to emphasize a little bit over here is what Shin was mentioning. You need to be able to recover your status at any given point of time, because for those who are familiar with the API server, if you create an object, it only creates a spec. You need to call another set of API to update a sub-resource in the for the status. The problem with that is that after you create a spec, your second call to update the status could fail. So in many cases, not in many, in rare cases, your status may get lost. And that's thanks to the idempotency the CSI driver maintains. So based off the identity of those objects, we were able to call the creation API or list API based off the same input, such that we can obtain back the exact information and to repopulate all the status. So the snapshot handle will be there as long as your CSI driver supports idempotency. With all this in mind, we start thinking a little bit more. One thing we were thinking is if we think about this alpha controller architecture, basically it works like this. We have a very nicely written script to serve as an installer. The first step is I go ahead and create a cluster role binding. And this cluster role binding will allow the controller to have access to both a namespace object, which is volume snapshot, PVC, et cetera, and a non-namespaced objects, for example, PV and volume snapshot content, et cetera, and then go ahead and bind that cluster role to a service account. And within the code, the controller actually generates a CRD and it registers with the API server. That's basically how it works, right, in the alpha. Now this looks perfect, it will work until you have two, right? If you have two CSI providers, meaning that it's very possible that you have two storage providers. One of the big problems is that, okay, we first need to make sure the cluster role names are different. Otherwise, you end up with a conflict and you won't be able to start your pod. And then the bigger problem is they will both try to register a CRD with the API server. Now, if these two CSI providers happen to deploy a different version of the controller, then you have a bigger issue because the CRDs may not necessarily compatible. So when we look at all this architecture, then we started thinking, and when engineers start thinking, that's normally the problem comes, right? And we figured out there are a couple of challenges we are facing with this architecture. The first one is deployment. So you will end up deploying could be duplicated CRDs with different version. RBAC rules is hard to set up, et cetera, et cetera. And the second thing is that how do you even collect observability signals? You have two or even more multiple CSI driver providers hosting exactly the same binary, but where do you report the metrics to? And how do you combine them together? For a cluster administration point of view, how do I aggregate them together to make sense out of it? And third thing is that any controller release, anything, I mean literally anything, the storage vendors needs to get involved because they need to update the YAML file and change the deployment in the site. So how do we try to mitigate this problem? We split. So if one controller cannot do the whole thing, we use two, basically. We introduced a new controller, which is called Snapshot controller. That's basically a cluster level deployment, which coordinates with all the CSI plugins, CSI sidecar drivers. It conducts complex Kubernetes logic, for example, object binding, snapshot binding to a snapshot content, et cetera, et cetera. It periodically scraps the VolumeSnapshotContent and try to update the status in the snapshot. This guy is not aware of CSI. It's completely within the SIG storage's control. You can release separately. There's no problem, as long as you don't make any backward incompatible changes. And there's a sidecar controller. And this guy, we try to limit its access for many, many reasons. One reason is that for security. And this guy only conducts CSI calls, and it only works on the content object. More specifically, it only works on the status of the content object. All it is doing is I watch content. Whenever there's a new content or there's something I need to reconcile, I go ahead and invoke a CSI call. I get all these stats back. I repopulate the status. My job is done. And of course, deletion is a different story, but deletion is almost the same thing. The key idea over here is to keep it simple. So you guys probably will be asking why this will solve the problem. It won't, right? It won't solve the problem in a very general way. However, it did mitigate the problem. For example, the sidecar controller is so simple that we don't expect it to upgrade from time to time, right? It's going to be a very, very stable binary that you can choose to deploy over the time. And the metrics side, at least we have a centralized place, which is the common controller to give you a metrics endpoint and under control of the system admin such that they can go ahead and scrap all these metrics. With all these major changes, I will move to Shin to give you guys some nice demo about the end result.
Thanks. So to use the snapshot beta feature, first you will need to install the snapshot beta CRDs. And also you need to install the snapshot controller. And this two installation are the responsibility of the cluster deployer. And then for the CSI vendor, you need to install the sidecar CSI snapshotter with the CSI driver. I'm going to show a demo. All right, trying to figure out. What's the button to should play? Should be play button should be here. I don't know why it's not.
We're experiencing some little technical issue here. Maybe you see
No.
with it.
No, then you are not.
Where is it? So,
Well,
your secret. Come over, please.
No, I think we need to go back to that. We need to go back to that view.
No, you lock here. The video is not showing up. Yeah, it's there.
Yeah, but it's not showing here.
Oh, you didn't duplicate that.
It's just,
So a little bit more.
Yeah, it's just okay. Okay, we'll just do it this way. All right, I'll just do it this way. Sorry about that. Oops. Yeah, so basically, we are trying to, the first step is to install the Snapshot beta CRDs. So we have 3 CRDs, volume snapshot class, volume snapshot, and volume snapshot content. So this is the volume snapshot CRD definition. So we install that. So now get all 3 CRDs installed. Next step is to install the snapshot controller. So here we have the RBAC rules and also the deployment script. So in the setup YAML file, we are using the snapshot controller image. So we are deploying the snapshot controller. So you see that all the RBAC rules are created, and we have the snapshot controller deployed as the stateful set. And the next step is to deploy the sidecar controller along with the CSI driver. Here is for the demo purpose, so we have the provisioner and the snapshotter together with the driver. So in this set of YAML file, we use 3 images. We have the CSI provisioner, CSI snapshotter, and also the CSI host path driver. As Michelle mentioned earlier, the host path driver is a sample driver, so it's not for production. It's just for demo purpose we're using now. So let's set up the CSI snapshotter. So now we got the cluster role binding created, and we have the CSI snapshotter pod created. So that's also created as a stateful set. So here you can see there are 2 pods running. One is the snapshot controller, the other one is the CSI snapshotter, which has the two sidecars, the provisioner and CSI snapshotter, and the host path driver. Okay, so now let's try to dynamically create a snapshot. So first we create the snapshot class. This is the storage class, and after that, we create a PVC. So PVC is created. And next, we need to create a snapshot class. So here we have a driver and a deletion policy in the snapshot class. Okay, so the snapshot class is created. So here we can see that there's a deletion policy. So that's actually now a required field now. And then we have all the information about the class. Now this is the YAML file for volume snapshot. Here we just reference that volume snapshot class we just created, and also under source, we specify the persistent volume claim name. That's for the dynamic provisioning. We need to specify the persistent volume claim name in the source. So it's created. This is the volume snapshot API object. So we have that source. And under status, we have the bound volume snapshot content name. And also we have the creation time, ready to use, restore size field. Now let's take a look at the volume snapshot content. So here we have the source, which is the volume handle. And we also have the snapshot class name, and we have the volume snapshot reference, which has information for the name and namespace and the UID. And now we also have a status field. This is new in the beta API. So this one has the creation time, ready to use, and the restore size, and also a snapshot handle, which points to the physical snapshot on the storage system. So now that is created. Next, we're going to try to create a volume from this snapshot. So here we specify the data source, which is we have the name, kind, and API group of the snapshot, which is actually the same as before. There's no change here, moving from alpha to beta. So now that is created, the PVC is created from the snapshot. So now we're going to try to do a pre-provisioned snapshot. So we have, this is the volume snapshot content. Admin will create this. So specify the source as a snapshot handle. This is for the pre-provisioned snapshots, and also specify volume snapshot reference. Need to specify name and namespace here. And then user will, so after the content is created, user will create a volume snapshot pointing to that volume snapshot content name. Okay, so that is created. Need to move to the next slide. Let's go next. Okay, so here is a recap of what we have shown in the demo. So for dynamic provisioning in the volume snapshot API, you need to specify the source, which is persistent volume claim name. So after it's created, we see the volume snapshot API object. So here you can see that there's a status, there's a new field there, bound volume snapshot content name. That's a new field that we added in the new API. Okay, and then in the volume snapshot content API object, now we have a status field, which is new. And then here we have the creation time, ready to use, resource size, and also now we have a snapshot handle in this status. So for pre-provisioned snapshots, so admin will create a volume snapshot content specifying the snapshot handle under source, and also specify name and namespace under volume snapshot reference. And then user creates a volume snapshot, specify the source, which is the volume snapshot content name. For create volume from snapshot, so we'll need to specify the data source, which includes the name, kind, and the API group. So this actually is the same as as before, because we didn't really change the PVC spec when we moved a snapshot API from alpha to beta. So we have a lot of work to do moving forward. So we need to add a webhook for validation, and we also need to add metrics for storage controller so that we can tell how long it takes to create a snapshot or delete a snapshot. We need to add more E2E tests. And also we are looking at volume group snapshots, how to create consistent groups. We're working on design for that. And also now there are a lot of people interested in volume backups. Now we have this basic building block of volume snapshot, so we're going to look at that. Then one specific feature is this change block tracking, which is pretty important for to get in the diffs between two snapshots, which is important for volume backups. So we'll be working on those, so have a lot of work to do. So yesterday I got a question. Someone was asking me why it took so long for moving snapshot from alpha to beta, because we introduced this feature in 1.12, and now it's already 1.17. But in the same time, the cloning feature moves from alpha to beta really quickly. So I just want to address that. So this is because volume snapshot has the CRD, and cloning feature does not have the CRD. And also for volume snapshot, we have a independent controller. So now we actually have two controllers after the split. And for the cloning feature, so we don't really need a independent controller. So we can just add extra logic in the existing external provisioner. So that's why it takes much longer to finish the volume snapshot work. That's all we have for volume snapshot.
Thank you very much. So next up, we're going to switch to a SIG storage panel. I'm going to ask Xing, Michelle, Sean, Jan, and Ben to come on up. And we're going to open up the floor to questions. If you have any questions, I'll try to be the mic runner. Maybe I'll hand over one of the mics to the folks on stage. Whatever works for you.
Don't stand.
First question.
I'm wondering what's the plan or recommendation guideline for future for a common scenario where people want to use snapshot as log shipping for cross data center, cross region backup restore. So for disaster recovery solution. So what's the plan and landscape looking like right now?
Okay, so I think we haven't really planned that far yet. So we just finished this snapshot bringing it to beta. That's like the basic building block, right? So we gradually adding feature to it to do volume backups. And then, so for what you were saying, if it's a disaster recovery, that would be something that we will be looking into in the future as well. Yeah.
So what's the timeline like? Oh, you don't really
We
have
don't
a
really,
roadmap
we don't
yet.
really have a timeline. It's way too early to talk about timeline. So if you just,
Yeah, on top of what Xin was saying, the data center and the recovery thing, it can be built on top of the snapshot functionality and the potential future backup functionality from the SIG storage perspective. However, I'm not sure whether SIG storage alone is gonna be the best party of building a whole backup and recovery system, because that involves a whole lot of knowledge is outside of the SIG storage domain. Correct me if I'm wrong, Saad.
Yeah, no, I agree. I think it is where we want to end up. We've been discussing it within the SIG for a while, but we need to get the building blocks in place first. And then we're going to work with our counterparts in SIG apps and folks from other communities to make sure that we have a solid solution. I think one of the biggest challenges with when you start talking about application backup is having to move data across storage systems. Right? With Snapshot and Restore, the assumption is that the storage system is consistent. And so being able to tell a storage system, take a snapshot and recover a snapshot within the same storage system is overall a kind of doable problem. Being able to say, please export this data to somewhere else, whether it's an object bucket or somewhere else, is a larger problem that requires Kubernetes to get involved in the data path somehow, and that is going to be a larger problem that we're going to have to think about how to address.
Just along the same lines, so a lot of the storage vendors support hardware replication. Is that something you guys are thinking of if you don't want it to be in the data path? But
yes. So there's a couple of ways to think about the features that we expose up into Kubernetes as hard-coded features, and those tend to be the ones where Kubernetes needs to do something special in order to make that functionality work. So if we talk about storage topology, for example, the Kubernetes scheduler needs to be aware of, where to schedule. Or for snapshots, when you provision a new volume, you need to be able to specify the source for that volume. For something like replication, as far as Kubernetes is concerned, it's kind of a storage level implementation detail. So the way that we surface it up is, if you look inside your storage class, there are a set of opaque parameters. It's up to each storage vendor to define what those parameters are. So for storage vendors that support replication, they can set that as a parameter like, hey, when I create a volume, please replicate it in this way. And in that way, you can enable replication with what we have today.
With the volume cloning feature, is there expectation that the clone will be standalone, or it can be kind of a child of the parent volume?
Who wants to take that one?
clone should be independent. So, but whether your backend storage has those dependency, that's up to your vendor.
Okay.
But from the Kubernetes point of view, it should be independent.
Yeah, when you take a snapshot, is there any hookups for the application to give the chance to flush their data? And basically once the snapshot is taken, basically give chance to hook up to they resume the data so that I can get a consistent snapshot and use the snapshot should be usable, right? Is there any hookups like that?
Yeah, so there is actually another proposal that actually is a cap that got merged called execution hook. So right now, it's actually he's not here anymore. So right now someone from SIG Apps is going to implement that. So we did a POC at the SIG Storage. We designed that. So that hook can be used to do QoS. So there's another feature, I think in Michelle's slides show that it's called application snapshots. So that feature will be using the execution hook to do the QoS. I'm sorry? Yeah, so the application snapshot is right now is a cap. That's still being reviewed. Execution hook is already, the cap is merged. We have some POC code, and then somebody's going to work on implementing the real controller.
The way that we think about it is that the snapshot API is the building block that we're going to be able to build a lot more on top of. So just the ability to poke the storage system in a consistent way without having to know what that underlying storage system to take a snapshot and then use it to restore is a powerful building block that we're going to be able to unblock a lot of functionality in the future. So one of the things that we want to tackle is, hey, I have an application, it is actually using more than one volume. And so when I take a snapshot of that application, it's more than one volume, and I want that to be consistent across all of these volumes. How do I do that? And so this execution hook KEP is a piece of that by saying, hey, here's a way for an application to specify how to QS the application and flush the writes. And then there's a larger KEP that's in the works or is coming soon through SIG apps to define at an application level, how do you create a snapshot?
Just to get a better clarity on the replication question the gentleman has asked earlier, did you say that for CSI driver integration, let's say for persistent volume, is totally independent of the replication that a storage vendor is doing at the same persistent volume?
So replication is independent of what's going on at the higher Kubernetes layers. So at the CSI level, the storage vendor can expose a opaque parameter through a storage class. So if you look inside the storage class object, there are a set of opaque parameters. It's completely up to the storage vendor through the CSI driver to define what those opaque parameters are. You know, it could be something like, what is the speed of the volume that's going to be provisioned? Is it an SSD or a local disk or something like that? But it can also be replication to say, hey, this volume is going to be replicated in 3 places instead of a single copy. And so as far as Kubernetes is concerned, it doesn't understand what those parameters are. They're not programmatically understood. But as far as users are concerned, they have a hook into the storage system to be able to manipulate and set these options that are unique to that storage system. And so in that way, if you have a storage system that supports replication, you just have to make sure that in the storage class for that CSI driver, you set the bit that says, you know, enable replication.
And is that how the hyperscalers are doing, let's say for GCP or AWS? Are they using the similar approach in order to replicate, let's say, from Azure files to, you know, cross-replicate?
Are you talking about replication across?
Of the persistent volume to a Kubernetes container.
Replication of a volume into a Kubernetes container?
Yeah, so scenario is you have a persistent volume mapped to a container controlled by Kubernetes.
Sure.
And assuming it's at the back of, let's say, it's on AWS or GCP.
Mm-hmm. Right.
Is that how Google is doing it? The way you mentioned about the opaque parameters?
Right. Well, so for replication, this is how it works. So for example, with GCE persistent disks, there is a parameter that allows you to say, please replicate across zones. And in that way, a GCE persistent disk can be set up to do synchronous replication across 2 different zones. And when that persistent volume is created, the GCE PD volume plugin decorates the PV object such that the Kubernetes storage system knows that it's available in both of these zones using the topology feature that I talked about. And so therefore, if the volume goes, an entire zone goes out for whatever reason, the Kubernetes scheduler knows that this volume is not just available to nodes in this zone, it's available to nodes in the other zone, and is automatically able to fail over to that other zone.
Thanks.
Mm-hmm.
So again, returning to the replication scenario, if I understand correctly, the current solution is only valid for inter-cluster replication. So if I want to DR remote site, my cluster needs to be stretched over there, right?
So the current solution works both inter and intra-cluster because as far as the Kubernetes layer is concerned, we don't care what the storage system does under the covers. And those parameters are opaque.
But I would need to restore the volume on the remote cluster, restore the pods.
Yes, that would be a manual process, right? If you have a Kubernetes cluster, within that cluster, you can set a flag to say, please replicate this somewhere else. And then if you want to pick it up and use it somewhere else, then that's the responsibility of some outside system.
Okay. So the topology, the volume topology will help me understand that this pod is running in the remote site and this pod is running in
Volume topology will help Kubernetes understand if it spans multiple zones or regions or whatever,
But not different clusters.
but not within different clusters, right? So it's within a single cluster.
Yeah.
I have a question related to snapshotting. So is there any work going on around versioning of snapshots by taking diffs? If I have a regular snapshot schedule, right?
So we are planning to support like the change block tracking, so if you have two snapshot, we want to get the diffs between the two. So that's something that we are thinking about supporting. What is the second one?
Are you asking about scheduled?
Oh, schedule. Oh.
Yeah.
So that one we have not really taken into consideration. I think that needs to be a little bit higher level. Maybe like at the application level, we could do. Maybe at the application snapshot level, we could do that. Yeah.
I know Jing wrote a prototype like a year ago, defining a CRD with a snapshot policy, and you can say things like take a snapshot every day, every hour, and it was a really easy controller to write to do that, built on top of the VolumeSnapshots API.
And before I take the next question, it's really exciting to hear questions like that about like what functionality is coming to snapshots and things like that. And I wanted to go back to something that Xing said earlier, which was she was apologizing for snapshots taking so long to move to beta. But I want to point out, it's primarily Xing, Sean, and Jing, 3 people who are driving this feature. They're coding it, they're writing all the end-to-end tests, they're doing the deployment, they're doing everything for it. And seeing all the excitement in this room about this feature, I want to see all of you in the SIG helping build these features. Help us code these things, right? Please show up. That would be awesome. Patch is eagerly accepted.
With that, I think there's no more questions.
There's
No,
a
I was
question
kidding you.
No, congratulations for all the work on the snapshots and everything. That's very cool. My question is a bit naive. Maybe it's not even belong here. Maybe yes. So let me know. I'm very interested in raw volumes because I can specify file system formatting and mount options, which are critical for what I do, which is databases. Now I'm even more interested in ZFS. And ZFS also requires a kernel module, which might or might not be present. Is there any way, any point at Kubernetes where API where I can specify I won't need this module or this support from the kernel at the host level to run the file system?
Ben or Jan, you want to take this?
Well, what I can say is no. There is no field anywhere in Kubernetes where you would say requirements on the operating system or on the host. What I can imagine is that you could deploy a daemon set that will inject the module, but then you need to get the volume from somewhere, compile it, or you need to know the kernel on the host and this kind of stuff. So I don't think that Kubernetes is the right vehicle to inject modules on the host, and that should be considered before installing Kubernetes on top of something.
That said, I have seen folks installing kernel modules through a daemon set. It is very painful, it's difficult, and there are lots of assumptions that are made. It is possible, but in general we recommend against having to install kernel modules through Kubernetes. Either your environment should have it already, or try and use something that is already very widely adopted.
I agree. It's a terrible idea, and it sounds like too low level against the somehow high level APIs of Kubernetes. But at the same time, ZFS is a file system that provides so many cool features that it's a real shame that there's no option to leverage it. So,
well, you can get ZFS into mainline kernel, and then it's everywhere.
That's the tougher way to
know.
do it. I don't disagree with you. It's just that involves much more than that.
And again, this might not be a good question for the group here, but as an array administrator, one might be worried about resource allocations, and not sure if that should be set at an array level or a storage provider level or within inside of Kubernetes itself. You know, maybe a Kubernetes operator would like to set a maximum resource allocation to like a per pod or a per namespace, and an array administrator might want to be able to set that at a cluster level. Obviously, the CSI driver can maybe send namespace or pod information, and it'd be up to the array provider to do with that information what they would to be able to set resource limitations. But has there been any thought about not exhausting a storage provider from somebody who launches 1,000 containers with 8,000, each one with a 1 terabyte volume hanging off of it, and they start writing storage out? Same thing with like a resize, growing the volume. How do you prevent the array from basically getting DDoSed?
What we have in Kubernetes is quota. You can limit number of persistent volume claims that a namespace can use. You can limit the total size of these volume claims per namespace. So you can limit each namespace individually, depending how important they are. And another thing we have on node level, and each CSI driver can tell a node how many volumes it supports. We call it volume limit. So if a driver says, for example, on AWS, a node can handle, I don't know, 39 AWS EBS volumes, then the scheduler then schedules only at most 39 volumes on that node. But that's basically all we have, right?
Go ahead.
There is actually a cap. Actually, there are 2 caps right now trying to get the capacity information from the storage system so that the scheduler can be aware of it. This way can address your problem. So,
But I think for your use case, it sounds like storage class quota can address it. Like as an administrator, you can restrict namespaces to some total capacity or maximum number of PVCs.
And that's something supported right now? Okay.
Yeah, it's been there for a very long time.
Very, very long time.
The new feature that was discussed was basically automating a way for the storage system to be able to say, hey, this is the capacity of the storage array that's available to me. FYI, I can, have 200 terabytes or something like that.
And in addition to quotas, individual CSI drivers can have limits on what they're going to expose. So like, different CSI drivers are built on different things. Like if it's built on GCP, you basically have infinite storage, and Google wants to sell you more storage, so they're not going to limit how much you can consume. But if you have physical boxes, the CSI driver is responsible for saying, okay, this is how much of the box you can take up, and maybe it's 100%, maybe it's less.
The use case here for us would be that we are an internal Kubernetes cluster with Pure and VMAX arrays that support critical workloads, and making sure that there's fail-safes from exhausting the array of its capacity, if something were to run awry.
Makes sense. I think the storage quota would help you there.
Yeah. Well, and make a feature request to whoever maintains that CSI driver to say put a cap on it. Like I work for NetApp, we have aggregates inside our storage cluster, and you can limit the CSI driver to only consume one aggregate and doesn't touch the other ones.
Thank you.
Hi. So congratulations first on all the hard work. From the clones topology, one of the questions that came up. So is the intent that when a clone is being created, it could be a full-blown clone, or it could be a thin clone, right? It's sharing resources. So is the intent that the storage provider will be managing all of this? Because if we are talking about, let's take a simple use case, repurpose use case, right? I'm spinning up 4 clones, and one of the patches is successful, I just restore it. So in this use case, the lineage needs to be tracked. So is the intent that the storage provider will be tracking all of that, but nothing gets bubbled up onto the CSI driver level?
Yeah, I mean, Kubernetes doesn't care about how the clone happens, just that it does. So
the only recommendation we have is to make it quick and efficient. But again, that is a strong recommendation, and ultimately it's up to the storage system what it wants to do under the covers.
Okay. Another question was ready to use was one of the attributes that was presented. Ready to use, is it like you can perform I/O or you can use to create other volumes out of it? What is the purpose of that particular attribute?
Maybe
Ready
Sean,
to use.
you want to answer that, or Shing? Okay.
That's a very good question. Thanks for paying so much attention to the details. Yes, ready to use, once marked as true, you can safely use that snapshot to recover a PVC. That's basically what that flag means. There's a little bit of history on this field. You know that in the Kubernetes world, in the cloud world, when we have a persistent volume, when we take a snapshot, a point-in-time snapshot, it actually cuts a point-in-time snapshot and uploads to a remote object bucket or something like that, right? And in this uploading period is significantly long if your volume is huge. So we don't want to hand on that for the applications because normally applications need to queries. And that's the reason why we introduced that flag telling application, hey, your snapshot is card, right now it's uploading, but it's not ready to use yet. But once the uploading finished, that flag will become true, and that means you can safely use that snapshot to recover a PVC in another namespace or whatever you want.
Yeah, in short, this is kind of thinking ahead to the QS on QS for application feature, where we want to be able to say, please take a snapshot storage system and let me know when the snapshot has been created, but you can go ahead and upload or do whatever you need to do. The snapshot may not be immediately available to use, but when you give me that first signal, it's a signal for me to know that I can resume the application safely. And I can resume the application, minimize that downtime for the application, and then whatever the storage system needs to do in order to prepare that snapshot, it can continue to do that in the background, and then give me a final signal with ready to use to say, oh, the snapshot is now ready to consume and create new volumes from.
Any more questions?
All right, well, thank you so much for showing up. And again, I'd love to see all of you show up more regularly to the SIG. Thank you.